So back a few years ago, um, when I first started doing experiments with radio astronomy, I started, as many do, with hydrogen line observations of the Milky Way using a very small antenna, a very simple setup. Um, and I, I wanted to have something to compare my spectral data against, and so I did some searching and found this all sky survey done in hydrogen, mostly looking at mapping the Milky Way, and um, and it and this is what I actually used then to first compare some of my very first observations, and I can't even describe how thrilling it was to look at my first observations and just see that the basic shape of the spectrum was the same as the professionals, and I was like, wow, it's working. And then of course it got more complicated from there, but as Edward and I both have in the past couple years been doing drift scan observations using small, like 3 meter sized dishes to um, to capture spectra of nearby galaxies outside of the Milky Way. And this was something that I was kind of on a quest to do to see if it was even possible. And one of the problems was then finding a way to there were a few papers, a few uh, professional survey papers that had integrated spectra of the nearby galaxies published. And so that was one reference that I used initially. But one of the things that Edward and I both kind of, I don't know if we independently came up with this or collaboratively. I remember talking about it a few different times on several of the virtual Drake's Lounge meetings over the last year, but we began to wonder if the data to simulate drift scans from a small dish was actually hidden inside this lab survey database. And because it was intended mostly for simulating observations of the Milky Way, but it was looking at pretty much the whole sky. And so we both kind of started experimenting with the data, and indeed we found that if we kind of matched the same procedure that we were using with our drift scans, that we could kind of simulate what a drift scan with a 3 meter dish would look like, and and that was pretty exciting. So I'm going to kind of go through how the method that we used. So
Jason, do you have a button to make that full screen? We see the next slide also.
oh, okay, yeah, let's see if I can display settings. Let's do
It
no.
said swap to slideshow. That might be the thing.
Well, I actually did go in slideshow. I'm just wondering why
The
it's
display setting had a swap to slideshow.
oh, swap to
Up at the top, display settings.
uh-huh. Oh, there we go. Okay. All right.
Much better. Thank you.
Yes. Okay, there we go. So this is what the front end of the user interface for accessing the database looks like. And basically you can select your coordinate system either in galactic coordinates or equatorial coordinates. I usually use equatorial coordinates because when we're looking at extragalactic sources, it's just easier using those coordinates. It makes more sense. Um, and then you can select a virtual beam size that you want to simulate with the data, and then the front end or the this software application then will basically do the math on the raw data in the database, and give you a spectrum that you should expect from from an antenna with the beam width that you select pointing at the position that you select. And then you just basically click search data and it generates a profile and allows you to download that profile as a text file. And so that's what we did. And you can go up as high as I believe the maximum beam width is 25 degrees. That's what I would use when I was doing, my when I was trying to simulate my backyard Milky Way setup with the Cube reflector because it had a very wide bandwidth. But when we're simulating drift scans with a 3 meter dish, we choose something around 5 or 6 degrees. Um, One thing the site says is the larger the beam width you select, the more computationally intensive the action is, and so it takes longer for it to generate the plot, and sometimes it can actually kind of choke on it. So, but anyway, so that's how the front end works. This is what a typical spectral file looks like that you would download from the site. It has kind of the metadata at the top, and then just has velocity column followed by a let's see. I'm trying to think how we did this. So I believe it was velocity, and then kelvins, and then frequency, and then there's a wavelength, and basically we only used the first two columns for what we were doing. So we wanted to plot velocity, plot uh, power and flux in kelvins versus Doppler velocity. Um, And then what I did for my analysis is I used the similar method to what I was doing on my drift scan observations. I used Excel to do my analysis, and it's kind of low tech, but I kind of like the fact that it makes it very accessible and easy to explain to people, and there's nothing hidden behind a complicated software layer. So that was one of the motivations that I had. Um, but basically, what I would do is uh, download profiles for fore and aft observations, and then a profile for on target. And then I would do the same thing I would do with my actual drift scans. I would average the fore and aft together, use that as a reference then to compare against my on target. Um, And then here's a side-by-side comparison. So the top is my observation data from my three meter dish of M33, and the plot on the bottom is the simulated observation generated by the lab survey data, and you can see there's a pretty stark, a pretty good agreement there. So this was a kind of uh, a very a good test of the concept, I guess. And then what I ended up doing was taking that and generating plots for M31, M33, IC 342, and M101, and kind of overlaid them all on the same plot with the same scale to kind of see. We were kind of wanting to, one of the things we were wanting to use this for is to kind of gauge how difficult an observation would be, based on ones that we knew we did already. Would it be possible to go after small, fainter and fainter, or farther objects? And so as you can see, they kind of go down. M31 is by far the largest, and they kind of decrease by half, more or less, as you go. Um, Now, one thing to notice on M31 is because its spectrum is so wide, we're only seeing the red shifted side, and about half of the spectrum. And the reason for that is that the lab survey database only has a spectral width that covers about plus or minus 400 kilometers a second. And so, unfortunately, some of the some of the galaxies that are nearby are Doppler shifted enough out of that range that we can't use this method with this data set. And that's one thing I reached out to Dr. Herman about this to see if in fact the data was limited to that bandwidth or if it was just the user front end. And it appears that the data itself is limited to just that range. And so if we wanted to do this kind of simulation with a, for galaxies that have red shifts or blue shifts outside of that range, we would need to use a different data set. I believe there are some other maybe more recent surveys out there, but I haven't been able to see that we have access to those easily yet. So something maybe to look into for the future, though. And now I'm going to turn it over to Edward, and he's going to talk about some of the stuff that he's done with this as well. So.
So yeah, so as Jason mentioned, we both came up with this method around the same time, perhaps together indeed. But whereas Jason is mainly using Excel for plotting and data processing, I am using mostly Python because I usually have like huge numbers of spectra to process, and at some point it just became too cumbersome to do so in Excel. So here's a screenshot of the code that I use to simulate drift scan spectra of galaxies. So yeah, I'm starting from the same data. So I download text files for the simulated spectrum from the lab survey page. Um, Before and after the transit of the target, and of course for the target itself. So yeah, in this code, I then first, of course, define the file names for these text files. And then I use the numpy mp.gen from txt function to import the data from these text files and write it into NumPy arrays, so I can do some numerical processing on it. And then the actual calculation that is just really simple. It's just as Jason explained, same thing that you would do observation. So you average together the pre-transit and the after-transit spectrum, and you subtract that from the target spectrum. And then, like this last little block of code with also all of these PLT dot statements, that is just for plotting. So this is using the matplotlib or pyplot library. And so on the right, you can see the plots that we get out. So this is an example for IC342. And so you can see this nice simulated spectrum. So now we can go to the next slide. Thank you. So what we can then do is that we can also import our own data from my own radio telescope and plot it together with the simulated spectrum. So in this case, I've taken one of my own results. This was from an average result from 7 drift scans of IC342 that I recorded last winter. So this is one of the weaker galaxies that is really like on the edge of what you can detect with the 3-meter dish. Yeah, as you can see, the signal to noise ratio is not super good, but you can still recognize the peak at around 100 kilometers per second. So this is the redshifted horn or peak of the galaxy spectrum. Blue shifted part overlaps with the galactic hydrogen in our own Milky Way, so we can't see that. And then also the slope towards the more redshifted side of the spectrum also matches up really nicely. So this looks like a positive observation indeed. So that was it. Are there any questions?
First of all, thank you very much. Any questions in the room? Or online? Any questions from the online folks?
Maybe just a comment on the availability of data. The survey that you've been using is limited to the range, so as we discussed previously. The more recent surveys, they're also available. You can also do the same simulation, but unfortunately, because they're much higher resolution, they are limited to 1 degree beam width. And also they're limited to 400 kilometers, but I know they have been recording a wider bandwidth. So the way to go is to request from the university eventually the certain cubes of data, which we can then integrate yourself. I'm not sure what is already available from the publication or not, but that would be the way to do it, to take the more recent surveys and then get a wider range, but that's not directly available through the website.
So I have a clarification question for me. When you say simulated data, is it actual observational data that's available, or does it literally simulate the data? So it's not real data, it simulates data.
It is real data, but what we're doing, the data was collected for a different purpose. And so we're using that data set to simulate the conditions that we expect with our drift scans, because we know the data is representative of what would actually be in the sky, even though the data itself was collected at a much higher resolution. The front end on that site allows us to it basically does the math to simulate a lower resolution view, and so we can so it is real data. We're just manipulating it to simulate a lower resolution observation, I guess.
Yeah, so to add to that, I believe that the data for the lab survey was recorded with a 25-meter dish. If I remember correctly.
I believe it
like
was
that.
3 different sites, right? It was I think that's where that's where lab comes from. So Leiden, Argentina, and Bonn all kind of collaborated on that, I believe.
Okay, yeah.
Very good. All right, thank you, gentlemen, very much.
One more question or comment here. I'm wondering what the effects of side lobes on the antennas are. The side lobes always seem to be kind of unpredictable on antennas. Does that cause some of the minor discrepancies you see, or what?
Not sure. I don't I think the signals that we're looking for are so tiny that we're only seeing, I think we're only really seeing what's in the main lobe, because it's you know,
Maybe I can add a bit to that. The data itself is side lobe corrected. They have done quite some work to compensate the effect of a side lobe. For example, if you're looking in a low density hydrogen area, but in your side lobe you have the galactic plane, then you have substantial intensity. So if you have a deviation under those circumstances, in your case, that might actually be somewhat that comes into your side lobe, which is not represented by the, let's call it the cleaned data.
I see. Okay.
For example, just as a side note, if we look at Lockman Hole, which is essentially has no hydrogen, with our 25-meter dish, we do see hydrogen, but that comes into our side lobe.
Ah, I see. Okay.
So I
Yeah,
have a question also. So did you, as a result of using the simulation, and then you got your data, did you find yourself finding errors in your results or trying to adjust things to make it match the simulation? And for instance, the noise level from your dish.
not really. I mean, it matched pretty well, but basically, uh, we were using this as a gross gauge to see what the size of the signal would be relative to mainly for, at least in my case, I was wanting to kind of see, um, based on the lab survey, what would it predict would be the relative difference in signal strength for different galaxies? Because I already made a solid detection of M31 and M33, so I wanted to see, okay, what should the relative reduction in size be expected for, say, M101? And and so what to me what this helped me do was to definitely uh, put the nail in the coffin of the additional 4 galaxies that I had on my first paper last year. I really think I'm 100% confident that the detection of M31 and M33 were real. I'm about 70% confident that my M101 was real, and the others were just bogus. They were way too large. They weren't, based on the lab survey simulations, they would have been so much smaller than what I was seeing. And so I knew that it gave me a gauge. It was more of like a sanity check, a gross sanity check to say, okay, am I just fooling myself or do I have a real detection? So in my
Jason,
case,
that,
it eliminated some of my false detections.
Jason, what is generally going to be a false detection? Is that, aircraft or RFI or what is that then?
I think it's just um, the fact that at really low levels, the background is variable. You've got noise, just
Heat sources.
variations, fluctuations in the background. And so I don't know that it's really caused by a particular source. I think it's just almost like statistical anomaly that the motion, the variation in the background over time and the, everything stacks up a certain way that it makes it look sort of like it's peaking in the right place. And
Yeah,
So just error,
what'd you say?
magnification of error, or additional, adding on error.
Yeah, I mean, one of the things is, we we can be biased to look for what we're looking for too, and once you think you got it, you kind of stop messing with it. And what you find is you can also be throwing away bad data and keeping good data, quote unquote, which biases your results too. But that's a difficult, that's kind of a difficult area too, because there are times when we get uh, just a bad scan that doesn't have good data in it. And so it's kind of like, knowing when you should consider it a bad scan that day, whether you had RFI or whether you had something that's I mean I've had, even with M31, I had times where for whatever reason the data just didn't have anything good in it. And I don't really have a good explanation for that other than the fact that maybe my dish was so flexible and portable that maybe the dish was out of shape and it wasn't pointed the way I thought it was. There could be a lot of reasons why that a particular observation turned out to be unsuccessful. And a lot of this was a learning curve too, of learning how to get the optimize the dish and get it functioning, and then learning how to optimize the observing, the method for observing with such a low-tech system as well. So there was definitely changes to my procedures over the months as I kept doing it more and more.